Good afternoon. Very warm welcome to the Oxford Martin School. Fantastic to see such a huge turnout. We are delighted to have Professor Sir David Hendry talking today. I have a long list of achievements, and I'll just give you a flavour of these. His role here at the Oxford Martin School is as Director of the Programme in Economic Modelling at the Institute for New Economic Thinking. He's also Co-Director of Climate Econometrics and Professor of Economics at Oxford. He was Chairman of Economics Department at Oxford from 2001 to 2007. He was Professor of Econometrics at LSE. He's had visiting appointments at Yale, at University of California, and at Duke. He's been the Honorary Vice President and Past President of the Royal Economic Society. He's published more than 200 papers and 25 books. He has a Lifetime Achievement Award from the ESRC. He's received 8 honorary doctorates, and he was knighted in 2009, which makes him a wonderful guide to tell us about climate change, past, present, and future. So I'll hand over to David.
Thanks, Julian. Welcome to everyone, and thank you for coming. My talk's going to draw very heavily on the research of all my collaborators in the climate change econometrics that we do, but I'm not going to do individual attributions, partly because none of them are here today, so they're going to... So, talk's going to try and describe the findings through our very novel approaches to modelling climate change empirically. These approaches come out of macroeconometrics, and they've been much more widely adopted in the climate and geophysics literatures than ever in economics, but partly because they come up with results that match what climate change people are expecting, but they don't match what economists are expecting, so they don't like that. Now, much of climate change analysis you read in the newspaper is based in physical models. They embody the many known laws of conservation, energy balance, and so on. But our approaches are complementary. We're using this powerful set of modelling tools to analyse empirical evidence. Now, the climate's evolving, but it's also subject to abrupt shifts like volcanic eruptions that I'll talk about shortly. But I'm going to begin long back as a background, where we haven't been modelling econometrically, but we have been looking at the background to emphasize that humanity can actually very easily affect the oceans and atmosphere. I keep meeting skeptics who say, oh, the Earth's too big for us to have an influence. I'll show you that's not true at all. We're having a huge influence, and actually it's obvious when you look at the data that it can be done. Then I'll consider the great extinctions that have occurred over the last 500 million years, which is going quite a bit into the past, as they're almost all due to climate change. And the reverse is therefore true. If we have a lot of climate change, we'll start seeing mass extinctions. Of course, none of these are anthropogenic. We were not around, but it's still the case that we need to worry about it. Given that background, I'll then look at atmospheric carbon dioxide levels and sea levels over the last 800,000 years of ice ages up to the present, move on to the Middle Ages and show how we detect the impacts of volcanic eruptions on temperature, because you need to take those out to get a good measure of the Earth's kind of equilibrium temperature in the past before the Industrial Revolution came along. Then to understand human climate interactions, I'll model the post-industrial revolution UK CO2 emissions, 1860 to 2016. Now, many people think the Industrial Revolution started in 1860, but in Britain it more or less ended in 1860. It started everywhere else because of the developments that happened in the UK. Then I'll illustrate the present by modelling the costs of misforecasting hurricanes. There's been a big cutback in the budgets of the US forecast agencies for hurricanes, which we think is a huge mistake given the costs from misforecasting them. Then I'll look at future climate after COP21, the impacts of 1.5 versus 2 degrees in temperature and output, and sea level rise. And then finally, we've been modelling climate change skepticism. Why do people doubt the evidence? So here we begin with the 2 key features of planet Earth. The atmosphere is this tiny, tiny, thin thing. It's roughly equivalent to putting a sheet of paper round a football. That's how thick it is. Can we change that? You bet we can change that. No problem at all. And what about the water? You read Blue Planet, you see there's massive oceans. That little sphere there is all the water on the Earth, all the ice, all the lakes, all the rivers, everything combined. That's all we've got. Can we pollute that? Can we make it into weak carbonic acid? Can we boil it? Again, you bet we can. No problem at all. Our resources are incredibly limited, and we're not doing a good job of looking after them. So let's go back 500 million years and see what's happened. Fossil record disappearances, extinction boundaries between all the various cases. It begins at the end of the Ordovician, and that's due to mass extinctions due to global cooling at that point. And the same is true at the end Devonian. That's when plants started to take CO2 out of the atmosphere and put in oxygen. And CO2 is very much a greenhouse gas, and so the Earth cooled very sharply, and many species went extinct. The worst is the end of the Permian. And this is probably from volcanic eruptions. The Siberian traps, which are about 300,000 cubic kilometers of basalt, were emitted. And it is believed they flowed into the shallow seas around the then united Pangaea and set off huge quantities of methane hydrates from warming them. And that then boiled the Earth very quickly, and you get enormous extinctions. Then we get the end Triassic extinction. This opened the ecological niche for dinosaurs to come in, and they spread, as you know. And again, it's massive volcanism, the central Atlantic magmatic province. And then the end Cretaceous one is the one that all the school kids know about. That's when the meteorite supposedly made all the dinosaurs go extinct. And that's wrong in several respects. First of all, there were also the Deccan traps were happening, and that's another 300,000 cubic kilometers of basalt in India. And secondly, the dinosaurs did not go extinct. Only Sauriscia went extinct. The Ornithischia turned into birds and are still around with us today. But these are mass extinctions, huge loss of species from the fossil record. So that's got us up to about the start of the ice ages, 800,000 years, and then we'll look at what happened to atmospheric CO2 and sea level over that period. So this is a 5-way chart. This is the CO2 levels over the ice ages as measured in various ways. They're reasonably accurate, there's some uncertainty, but not enough uncertainty to be terribly important. Then when Keeling starts measuring the CO2 by flasks in Mauna Loa, he sees that it's already well above anything in the historical record, and now it's above 400 parts per million. Now, what does a part per million mean to anybody? Well, a part per million is roughly 7.8 thousand million tons of CO2, billion tons of CO2. A ton is roughly 1,000 kilograms, and that's what you would emit from your car if you drove somewhere between 3,000 and 6,000 miles, which many people do 4 or 5 times a year. So they're probably emitting several thousand tons unknowingly from their car. And of course, you put in petrol, petrol's a hydrocarbon, and you put out carbon dioxide. That's combining the hydrogen and replacing it with oxygen, which is 16 times heavier. So you put out a huge weight. Here are the annual changes in CO2 globally, and I've put in the trend line because it's accelerating. It's not that we're bringing it under control, it's getting more and more out of control every year. And the parts per million we're emitting are now roughly 3 per year. And that's not going to take terribly long to raise parts per million to temperatures that are unsustainable. Here's what's happening to global temperatures. The one that's really worrying, and has been worrying for some time, is the Arctic. The Arctic's been warming much faster than the rest of the planet, and that's because there are internal feedbacks. You melt ice, which is white and has high albedo, reflecting lots of sunlight. You replace it with black sea, the sea warms up, that melts more ice, you get more albedo, and off it goes. And so it's a runaway, and it has been, as you can see, rising extremely rapidly. And then this is ocean heat. Now, back here, they're not fantastically reliable, but they are reliable enough for this to be completely different. And this is only down to 700 meters, and we now know that, in fact, it's been warmed far further down than that. So, what's doing it? Well, there are arguments that there's natural effects and there's human effects. So let's start with the natural effects. We've modeled spent several years modeling the changes, the emissions of CO2 in the atmosphere, and then we cumulate them. And the ones when we cumulate, the only one that's tracking the trend are anthropogenic emissions, emissions from factories, from cement, from farming, from transport, etc. This is Southern Oscillation Index, if you like, El Nino, La Nina. It has been going up. They've been getting bigger and having a bigger effect in temperature. But look at the scale. We're talking about from -1 to 2. And we're talking about from 340 to 380. So the scale is vastly larger from the human effect. And this is the natural effect, the normalized difference vegetation index. We've got pictures of the Earth from which we can calculate how much green there is. It's enormously seasonal, as you can see. The plants spring up in the spring and they die down in the autumn, and that changes the amount of CO2 they absorb and then return. But it's been trending down. It's been a nice offset, but again, look at the scale. I'm afraid it's only been offsetting by about 4 parts per million over roughly 25 years, as against 40 parts per million that we're putting out into the system. What about sea level rise? Well, let's go back to the ice ages for this again. And this is the last glacial minimum, when Manhattan's under about a mile of ice, right? It's only 4 degrees cooler than now. Think of that when you get told 2 degrees isn't much. 4 degrees led to a mile of ice over Manhattan. When it melted, we get this enormous rise in sea level, roughly 120 meters since the last ice age. Now, how do we square that with a tiny ball? Well, think of having a bath that's half full, and think of having a basin, a wash basin that's half full. Now take 10 litres and pour it in. It has an effect in the bath. It floods the bathroom if you pour it into the basin. Because there's so little water, it's really easy to change the sea level. And that sea level will have dramatic effects on all the coastal cities. About, I don't know, 1.2, 1.5 billion people living in them. What's been happening recently is also quite worrying. We can look at the sea level rise from 1880. There were tide gauges, not terribly reliable. There's a lot of uncertainty, but the uncertainty is completely dwarfed by the rises. And the rises recently have been based on satellite measures of how high the ocean is, gravitational changes, if you like. And we can see that the trend has been changing. If you were to draw a trend line through here, it would be here. If you draw it through here, it would be here. It's accelerating. It's the same problem. Not only is the amount of CO2 accelerating, sea level rise is accelerating. It's gone from roughly 1.3 millimeters per annum from 1850 to 92, now going up at 3.4 millimeters per annum. So we're going to cause flooding very, very quickly. Now, sea level rise matters because, again, let's go back to the bath analogy. Once we've poured our 10 litres in and the bath's a bit higher, imagine you were creating waves in your bath before someone poured in the extra 10 litres. Now you create waves in your bath. You'll see they're disproportionately higher because you're putting all that extra water level up in one pile. So the 1953 disaster we had in the East Coast, now, if we get the same strong north wind piling up the North Sea, then it changes to an east wind and blows. By 2035, it could be over the top of the Thames barrage. It's not very far away. One has to think very seriously about what we are doing. Okay, now we move on to the Middle Ages. We can see what's happening in the world. What was happening in the Middle Ages was, of course, as far as we're concerned, very important because there wasn't much industry. There wasn't much excess CO2 emission beyond the natural world. So if we can get the correct temperature for the planet in the Middle Ages, we can then compare what's happening today to that. Currently, IPCC use 1860 to 1880 or 1850 to 1870, depending. They're actually highly industrialized. They're not a non-industrial basis for getting temperatures to see what's happening. So we apply our methods to try and find where the volcanoes were. Now, temperature reconstructions are done in about 10 different ways. The people who've picked up our methods are the volcanologists and the dendrochronologists. And they've both got really interested because if we look at a graph like this, this is the Earth's temperature from about 1200 as measured from tree rings. You know, when there's very cold, tree rings are tiny. When it's very warm, tree rings are larger. And then you can construct the temperature from that. And then there are these massive drops in tree ring growth. And the question is, are they volcanic eruptions? And here's the current temperature, way out of the range that we've seen historically. Now, if we can find the volcanoes, we can then correct the dendrological temperature records. And the way we do this is what I would call completely objective. We could go out there and try and find what volcanoes have volcanologists discovered, right? They throw material up, the material lands, they can find out the timing, and then we could try and take out that effect. But we do it completely differently, and I want to spend a little bit of time and hope you've got the concentration to follow this, because this is how we do everything, right? Not just volcanoes, but how we estimate economic effects, how we estimate recessions, how we estimate climate growth, how we estimate CO2 emissions, and so on. Right, so here's Mauna Loa Observatory atmospheric transmission over the last 40 years or so. And the crucial thing with the volcano is it throws stuff up into the atmosphere, blocks the sunlight, reflects it back into outer space. The temperature drops. The temperature drops almost immediately because most of the material that comes out very early. Then it recovers very slowly. And you can see from El Chicon here, it's a very rapid drop. There's a massive amount of material put up. It lowers the whole world's temperature. And then it kind of recovers. You know, those of you who know your Greek know the Greek letter nu. It comes straight down, then it goes up, and then it tails off. So it goes up by roughly a half, and clears off. And Pinatubo is almost exactly the same, a rapid drop, and then it goes up. So if you wanted to discover volcanoes in this time series, without claiming you knew when they occurred, the way we would do it is we design an indicator that looks like this. It drops, and then it goes back up a half of what's left every time. So that's what this slide shows you. So what we have here is the average of all the volcanoes over the 900 years that we've got the data for from 1200. It goes back much further, but we're just modeling that period. And that's it's quite a wide range of reactions. And then the red line is the kind of Greek nu. It drops down and then comes back up. The orange is a volcano that erupts for more than 1 year. There are volcanoes that keep erupting and put up huge amounts over several years. And that's more like a U. So we create a V, if you like, a Greek letter nu, for every observation. So here we've got 9 observations. 4 before the volcano. We don't know it's here, but I'm just saying we've got them from 4, 3, 2, 1, 0, and then 2, 3, 4 after. And so we put 1 in, not all together, because we get a perfect fit and we tell you nothing, but in big blocks and search for them. But the ones that don't match a volcano are thrown out by the program. It's a kind of machine learning program. It says, oh, it doesn't matter, there's nothing happening. Then you get the one that hits the volcano, and then you get the ones after where there's no volcano again, and it drops off. I'm sorry, I gather I'm not near enough the microphone. Usually my wife complains about my booming voice, but... we do this. Imagine putting them in for the first 4 years, then the next 4 years. The one that hits will be retained by the program because it actually picks up this big drop in temperature. The others do nothing and they're thrown out. And you can try these as well. So this device we call indicator saturation. And we want to locate the significant drops, but we don't want to force them to match known volcanoes. So we do that over the whole period. So the top graph is the temperature graph you saw earlier. The blue line is the fit of the model. The model's got other features than this because other things are going on. And then the bottom line is the volcanoes that we find. And we find almost all the known volcanoes, right? And we find how big an impact they had, and we can show what's going on. Now, when people worry about how cold can a volcano make it, well, let's talk about Tambora, 1816. It's just recently been the centenary of the bicentenary of it exploding. It's the year without the summer. It snowed in New Haven in July 1816. July, anyone who's been to New Haven in July thinking that it's cold enough to snow knows the problem. Of course, it was a disaster for Europe because 1815 was the end of the Napoleonic Wars. And we also know that Frankenstein was written because Byron and friends were all locked in a chateau in Switzerland because it rained every day, it just poured. Now, when Somalis happened, it did exactly the same thing, a big drop in temperature, but it caused probably around 50,000 deaths within Britain, because in the first year, it rained so much the crops were destroyed, and the next year, people started eating their seed crops, but the third year, that's all they've got. And when the temperature improved in the fourth year, there's nothing. No crops to plant, no animals to breed, and they all die. And that's, fortunately, one of the things that no longer happens. Krakatoa, of course, is also famous. The other thing about Tambora, of course, are Turner's skies. If you often wondered these fantastic skies he drew, well, that's the reflection of the sunlight on the material thrown up by Tambora. It's lasted a long time. So how well do we do? Okay, so here's one particular one, just to illustrate that this can still be used. It's not a historical thing just to correct the temperature and get it out. Here is the impact of the eruption in 1641 of Parker in the Philippines. The grayish line is the temperature calculation. The reddish line is our model, and the blue line was the previous model, which you can see is pretty inaccurate. And you can see that we have to wait. We're not predicting the occurrence of volcanoes. Don't get that wrong. We wait till the volcano occurs. That then tells us how big the drop is, and then we predict what the recovery will be. And it's not exact, but it's pretty accurate and much more accurate than anything that went before. So if we get another world-class volcanic eruption like El Chicon, we can tell you how quickly the temperature will come back, which is quite useful for planning. So that brings us up to the Industrial Revolution, to the present modelling UK CO2 emissions. Now, the Industrial Revolution began in the UK in the mid-18th century, and there's lots of wonderful literature on why it happened, but the consequences of it are quite startling. Real economic growth in the world up till the invention of the Industrial Revolution was pretty much negligible per capita. Small developments due to the Roman Empire, due to the improvement in agricultural yields, but otherwise it was pretty much life as usual. Since then, real incomes have risen 7 to 10-fold in real terms per capita. I mean, absolutely enormous change compared to anything that went before historically. And that's allowed us to have research programs that have tamed killer diseases. Longevity has roughly doubled for humanity. So we've had enormous benefits, and they've spread right across the planet, as Max Roser's wonderful Our World in Data shows us. They're much bigger in the West because it began much earlier, and it hadn't, and it got the benefits of colonization, which some of the other countries lost out on. But the unintended cost has been a massive increase in atmospheric CO2 that I showed you earlier, going from probably about 250 parts per million to 400 parts per million. Now, when did people first begin to understand that CO2 was a greenhouse gas? Well, as usual, in the past, women did not get the credit for the discoveries they made. It was actually discovered by Eunice Foote in 1856. And what she did is a demonstration you can make today for skeptics. Get a flask of nitrogen, get a flask of oxygen, get a flask of carbon dioxide, put them in the sun for 2 hours, take them out and measure their temperature. Almost none, no difference in the nitrogen, none in the oxygen. The carbon dioxide's boiling hot. It's a greenhouse gas. She showed that in 1856. Tyndall did it in Britain several years later. Arrhenius gave a theory as exactly why it reflects back some of the emissions and causes the equivalent of it. And it's got very, as I've tried to emphasize, potentially dangerous consequences. Now, the Paris Agreement at COP21 is not perfect, but it's the first major development in those areas. And it's led to efforts to pursue 1.5 degrees of an increase relative to the 1860-1880 type period rather than 2. And I want to illustrate how climate econometrics works in a second example, which is modelling the UK's CO2 emissions over the period from 1860 to 2016 to disentangle the causes of those emissions and the role of policy, like our wonderful Climate Change Act of 2008. That's a real step forward, even if it's not a perfect solution. I also want to emphasize that the data we're modeling is very difficult data to model, right? So this is the UK CO2 emissions per capita per annum since 1860. It rises dramatically over the Industrial Revolution up to just after the First World War. It goes absolutely chaotic in the interwar period. The general strike, for example, has a massive effect. The US Great Depression has a big effect. The Second World War has a big effect. It rises again after the Second World War to the end of the 70s, and then it plunges. And it really plunges. It's now below anything that we recorded since 1860. It's a massive drop. It's gone down from about 11 tons per person per year to under 6 tons per person per year, basically halving. Sorry, over 12 tons to under 6, more or less halving. And one of the crucial things about it is, yes, prices of electricity have gone up a little bit, but real incomes have nevertheless more than doubled over this period. Now, you read articles saying, oh, the cost of dealing with climate change, it's dramatic, it's huge, etc., etc. The aggregate effect of reducing our emissions by more than half has been trivial. We don't know how much higher real incomes would have been, but they've doubled at least over this period. So it hasn't required large aggregate sacrifice. What's gone wrong is idiot government policy. It hasn't looked after the losers. Something all governments, even Labour governments, seem not to think about is who is paying the cost. If we're not paying it at aggregate level, somebody's paying it. Well, obviously it was coal miners for the most part over this period, because much of this reduction was due to the reduction in coal. So these are all the fossil fuel consumption figures. This is coal in red rising up and then plunging. It's now virtually gone from energy production in the UK, and it's still used in some areas. This is oil, Churchill's decision to change the British ships from using steam driven by coal to steam driven by oil, and it rose until the oil crisis, and then it's come down. This is natural gas, which came out of the North Sea in the 1960s and rose very, very dramatically. But you also notice it's come down, and then renewables. Now, renewables have risen very, very rapidly, but they're still very small in comparison to the other sources of energy. We've got a long way to go. Nevertheless, CO2 emissions are more or less dominated by what kind of equipment are you using. And I'll talk shortly about the switch from coal gas to natural gas. It brought in a huge increase in the use of gas in Britain, but it required a lot of change to the capital stock. This is a ratio of usage of energy producing CO2 relative to the capital stock. And over this period, it's fallen by 92%. Right? A massive reduction in the amount of CO2 we emit per unit capital stock. And that's partly because we've got more efficient everything. I mean, just whatever you're doing is more efficient. It's partly the changes in energy mix from coal to oil to gas to renewables. But nevertheless, despite this big drop, which, by the way, is almost identical to the drop in America. People often think the USA is way behind in its behavior, and it is in many respects, but relative to its capital stock, its emissions of CO2 have dropped by 90% since 1860, right? A very, very similar drop to ours. Now, of course, the capital, as Alex Pfeiffer and company have noted, is subject to the problem of stranded assets. People often think, well, what's a stranded asset? And given what's happening to sea level, I tell you now, it's a house in a new flood zone. That's going to be a stranded asset. Or it's a diesel car when diesel's banned. These are stranded assets. They're not the kind that most people think of. But if you want to think of things where you've put your money in and it's lost completely, they're going to come about because of climate change. So they're going to affect you as well as companies, right? It's not something, oh, other people will be affected by climate change, not me. You will. Okay, now, this is another way of trying to illustrate how difficult this data is to model. Right? When you see a time series of, say, GNP, you see little dips and drops from recessions and depressions, etc. But you don't see anything like this where it rises very dramatically, because most of the time the only source of energy was really coal. Then we get a big fall in the use of coal, but still CO2 emissions go up. And then we get a big fall in emissions, even though as well as coal falling, and partly all these other ones falling. But this kind of highly non-linear data is not something that you model in an afternoon, even with our software. So I want to show this in terms of a way that I think people might understand more easily. Distributional shifts. These are our total UK emissions in millions of tons per annum and the distribution thereof. So this is a histogram, which you did at school, and there's an interpolated density trying to represent that histogram, and that's the period from 1860 to 1899. Then if we go from 1900 to 1939, it's a very different shape, and it's much higher up in tons per annum. It moves right across. And if we go one more step, and we look at the period up to 1979, it's spread out a bit. Okay, there's certainly, that's the war doing some of that. But also, it's going up, and then, whoomph, it comes back down again, right? Quite a big drop. That's the yellow one here. That's the final period from 1980 to 2016. So I've tried to show you that coal has changed a lot. The relation of coal to things has changed a lot. Emissions have changed a lot. The distributions have changed a lot. So how do we tackle this? We tackle it exactly the way I've tried to explain for volcanoes. We put in all the things we think affect emissions. And here that's coal, oil, GDP, and capital. Right? These are the four main variables. And they don't all happen at once. There's dynamic relationships involved. And then we allow for all these shifts, right? All these shifts have happened. We're not going to argue where they happen or why they happen. We're going to put in indicators for shifts, different indicators. They're not going to be U-shaped. They're actually going to be step-shaped. So here I've done the same thing. So here's 4 observations before a step shift and 4 after. And if you were to put in the ones before, there's no step shift. This is the actual data. You could put in step shifts here. Nah, nothing's going on. Then there's a big drop. And it says, aha, there's a big drop. And then after the big drop, it says none of these matter. So we use this saturation method. And it only retains indicators if the model does not fit the data. Right? It will not pick up an indicator if the model fits the observation. Right? It doesn't need it. But if the model fits that observation, it probably fits lots of others. And so it dominates the explanation over putting in an indicator. And what do we find? Well, we find 3 very large step shifts. And when you look back at the archival record, they're clearly identifiable with major events. 1925 was the Act of Parliament creating the UK's national electric grid. And that hugely improved the efficiency of electrical appliances rather than lots of little places all generating their things and using even different measures of watts and amps, etc. 1969, I've mentioned, that was the start of conversion from coal gas to natural gas. And that leads to a huge increase in the use of gas because, of course, almost all houses in Britain can get connected up to the gas network. And then 2010 follows the Climate Change Act of 2008 because it only kicked in after a couple of years. Now, we don't impose those. That's what the data says. These are where you need step shifts over and above the explanation of the data from coal, oil, GDP, and capital. Right? These are over and above it. So this is how well we fit the total UK CO2 emissions. As you can see, the model provides a wonderful description of everything. And unsurprisingly, it also needs something to pick up 1926, the general strike, right? There was a huge drop in the use of coal and therefore in CO2 emissions. 1925 is the creation of the national grid. Now, you can't see these things in the graph. You can't look at the graph and say, ah, yes, 1925 indicates an improvement in efficiency. Yes, emissions dropped, but many other things are going on in the interwar period, right? The Great Depression, the general strike, the start of the Second World War, all these things. 1945 is another blip that the model can't explain why it dropped so much, given what the other variables are doing. 47 was, of course, an appalling winter. We haven't got temperatures in here, so it might have had an effect over and above. 1969 is the conversion of gas, and you can see emissions do go up for a period. We also find one at 1991, and I have not managed to find what went on at 1991, but what's surprising about 1991 is that the data have gone up, and it says they should have gone down, right? That's what the model says. We can't fit these observations because given what's happened to coal, oil, gas, GDP, and capital, it ought to have dropped and didn't. And then you start seeing the major drop here, 2010 on down. So we can actually find all the effects on UK emissions. So what about modelling the costs of misforecasting hurricanes? That's very much a US and Pacific area thing. It's not going to affect Britain. But it's to try and show you we can model the costs of misforecasting extreme events, right? We don't need to say, oh, we can't deal with tsunamis or whatever. We can actually model the costs of extreme events, including storm surges, etc. And misforecasting hurricanes is very good, partly because recently everybody knows that some of the hurricanes have been disastrous. Harvey, Irma, earlier than that, Katrina, Sandy on New York, etc. They've been very big and very important. And they're not the only cost of hurricanes, of course, but we can look at them. So of the 10 costliest weather and climate disasters in the US since 1980, 4 of the 5 occurred this decade, right? Is climate change having an impact? Well, you can't guarantee that's a cause, but it sure looks like a smoking gun, as American movies would put it. Does forecast uncertainty impact hurricane damages? Well, you would expect it to, because if people don't expect a hurricane to hit them, they're not going to take adaptation measures. They're not going to board up their windows, bring in sandbags, evacuate, or whatever. And if they do expect it, they're going to do these things. And so the impact might be a lot lower if they know that they're going to happen. Now, adaptation efforts are driven by belief. And these are all the hurricanes that have happened in the US relative to the 12-hour ahead forecast. So the actual location versus the predicted location. And these arrows, if it's green, it shows that it was slower than you expect. If it was orange, it was to the left or right, depending on which way the arrows are pointing. And if it's red, the forecast was too fast. And you can see they've hit all over the place, and there have been small forecast errors. But on average, these are the individual forecast errors, and this is the kind of band of forecast errors in the shaded color. And you can see that on average, it's been improving dramatically. It got a little bit wrong here. But for the most part, the US has got much better at forecasting where the hurricanes will hit, when they'll hit, and how big they'll hit, right? The 3 dimensions you would like. But increased forecast uncertainty does imply reduced adaptation, and we believe that leads to increased damages. So let's model it. And we're going to do exactly the same things as before, except now it's for hurricanes. So what are the things that might lead to higher damages? Well, people in the area have got higher income. There are more of them. There are more housing units. The historical frequency for that area might mean if it was unlikely, they weren't prepared. The wind speed and pressure, if it's higher, it's going to cause more damages. The maximum storm surge, if it's 10 meters rather than 5 meters, is going to cause more damage. The maximum rainfall, think of Harvey and what it did to Houston. The soil moisture, if it's already very wet, it's going to get more flooding. The air temperature, and then ours, the forecast uncertainty. But there are actually 35 other variables in the model that other modelers have used. These are the key variables. So we've got the data, and we've got very large numbers of variables. But again, we use machine learning. Our Econometrics program sifts through. If income didn't matter, it wouldn't stay in. What stays in? Well, in fact, only these stay in. None of the 35 variables that have occurred in other models stay in, nor did we need any indicators, right? There was a few, any step indicators of big shifts in what's happening. They're picked up by the income of the area, the housing units in the area, the minimum pressure, the maximum storm surge, the maximum rainfall, and the forecast uncertainty. It comes through as a major indicator of cost. The more uncertain, the bigger the cost. And Irma is just a beautiful example of that. It's forecast to go up the east coast and smash into Mar-a-Lago, but unfortunately went up the east coast, or the west coast, sorry, and it actually hit the people who'd been moved out of the east coast. and would have been much, much bigger than necessary if they had correctly forecast where the path would be. So how well did we do with Harvey? Now these are, again, the hurricane comes in, it causes its damage, we have our model. What does the model say will occur? What it says will occur is this blue box, that's, up here, the blue box is our average prediction. That's the official average, in fact, we're spot on. They're basing it on what hit Houston, the flooding, the housing destruction, the loss of income from factories closing, the swamps the sewage produced from the system, etc. The uncertainty is quite big, it's not enormous. Our uncertainty is much bigger, I have to say. Our model doesn't pin down exactly, but it gets it right on average. And there are two other existing models that don't have the forecast uncertainty in them, and they get very different predictions of what the costs of the damage will be in terms of billions of dollars. So we think we can help in that area as well. Okay, that's the present, then we're into the future. What can we say about the future? Well, we've been asked by IPCC to put in papers on 1.5 versus 2 degrees in terms of damages and on sea level, and this is the damages. It's very non-linear. If you deviate greatly in temperature from the average, you'll drop quite a lot. This is two possible measures, but they're very similar. And this is a picture of where the climate projection differences from no additional warming will occur. And as you saw already, the poles are warming much more than other areas. But I'll come back to a more interesting graph of the impact of warming in a moment or two. So we can work out what does 1.5 relative to no additional warming mean, and what does 2 degrees relative to no additional warming mean. And the purple shows you lots of loss of growth rate of GNP, and you can see where it hits. It's the tropics, it's India, it's South Africa, relative to what would have happened if we could keep it at 1.5. So it's really worth the effort to try and keep it to 1.5. There's a very big difference in terms of projected median changes in annual GDP per capita growth rates. Now, it's very different for the oceans. First of all, the sea's not level. Expansion of the oceans depends on thermal expansion. It depends on the currents changing, which might happen with the Atlantic meridian overturn. It depends on glaciers melting. It depends on the Greenland ice sheet, the Antarctic ice sheets, west and east. It depends on land water. And it also depends on whether it's uplift like Hudson Bay or subsidence like it's happening in all the major cities in East Asia. They all have an effect, but it varies very much geographically. Now, between now and 2050, we can be almost certain what's going to happen because the sea level changes slowly. Yes, it's accelerating, but it's not going to accelerate dramatically more. The results are baked in already, and we can tell planners what they need to do now to be ready for 2050. Beyond that, it's hugely open. There's a lot of great uncertainty. So this is the global sea level rise projections with strong mitigation, weak mitigation, and business as usual. And there is certainly a difference between even weak mitigation and business as usual, where you'll get very large rises of up to 2 meters across much of the world. For the 2 degree pathway, it's a bit less, and for the 1.5, this is up to 2100. So beyond that, you can see the uncertainty explodes after 2050. We get these grey bands of the uncertainty. But the 1.5 versus 2 for most of the period are relatively similar. So it's not going to, what we do now will not help us in terms of sea level rise. Can we model climate skepticism? Well, climate change does not imply global warming. I really want to make that very forthright. I've tried to persuade Nick Stern not to use 2 degrees, not to use global warming, only to use climate change. It's a change that killed off all these species 500 million years ago up until the dinosaurs. It was a change. It wasn't the level. The Earth's been vastly warmer and vastly colder, and species have survived. But thousands of species have gone extinct, and we don't want that to happen to us, and it's a change that does it. So if we look at the levels of this from May 26 to 16 relative to May 55 to 65, so they're both decadal long ones, you can see that they're much warmer in the Arctics and through the central, if you like, the Middle East and down in the Antarctica. But look at this. Look at this. It's cold in the US. Why is there much more skepticism when anything global warming's happening? Because they've had global cooling over this period, right? It's just one of these things that's happened. The Earth isn't perfect. It takes a long time to get into balance. They are observing in the Midwest, which is where disbelief is strongest, they've had a lot of cooling relative to the previous decade. So we've got to change it to climate change. Please, please, please. The words matter. So is there skepticism despite overwhelming evidence? Well, we've got here a graph. This is based on our modeling of all the counties in the US. And it's the number of days in a year for which the record high is more recent than the record low. And there's spatial variation over the period, and there's temperature variation. But you can see that, in fact, in areas that people experience higher temperatures and believe climate change is happening, they are in the two seaboards. And a lot of the middle, it's not happening, that's in blue or orange, where there's not much going on. So there is a basis for their disbelief, but it's not very good when the science says, look, mate, don't let anecdote dominate over science. We're the most educated generation ever in history, and yet everywhere you see people believing anecdote, whether it's in vaccines or climate change or anything, they believe anecdote over vast amounts of evidence, and it's terrifying that that's what's happened in this world of ours. Okay, so let me draw some conclusions just before Julian waves at me. Past mass extinctions are all due to climate change. There's now not a shadow of doubt. They're not us, it's not anthropogenic, it's totally natural, but now it may be us. The atmosphere and oceans are very easily altered by our interventions by emitting excessive CO2 and pollution. People have begun to focus on how much plastic there's in the oceans. Well, think of that little sphere and think of the amount of bags and rubbish we pour into the ocean every year. Of course it piles up. It's a really serious problem. UK emissions since 1860, we've emitted roughly 75 gigatons, or 10 parts per million cumulatively in this tiny little island. So yes, we've had a major effect on world CO2 emissions. We're now way down. It's now below the level in 1860. We're doing better than most countries in the world, and hopefully, now that we've almost eliminated coal and are starting to tackle oil, we'll do better still. But by being the workshop of the world, we've raised world living standards tenfold. This is 10 parts per million is actually a small price if only we'd stopped everybody else polluting the world in quite the way we did. Now, we did it when there were no alternatives. People didn't know about the internal combustion engine. They didn't know about the generator that Faraday came along with to get electricity. They didn't know about natural gas. They weren't available. They had to use coal. But after that, after 1900, you do not have to use coal. Prices and policy matter. Conclusions in econometric modelling. Well, we believe our toolkit has been very effective, and this has been shown by the number of people in the general climate and geophysics literature that have started using our tools. We can establish that there's a trend in atmospheric CO2 that's uniquely anthropogenic. We allow for everything that Henry's ever suggested naturally might affect it, and it doesn't. We can detect the impacts of volcanic eruptions and take them out of temperature to get a level temperature, if you like. We can model CO2 emissions despite all the major shifts, and we can show that policy worked. If you have a national grid, it's more efficient. If you introduce a better system of using gas, people use more gas. And if you bring in a climate change act that penalizes coal, coal begins to disappear from the system. We've shown that improved forecast accurate hurricanes can help mitigate their damages. We've estimated the cost of temperature changes from 1.5 versus 2, and we've linked climate change beliefs to local weather. There are many areas I haven't talked about, but we've also shown that actually many climatologists were quite surprised. Local emissions affect local temperature. If you put out more CO2 locally, you get a higher temperature locally. And that's because it's rather like a river. Yeah, the CO2 is a well-mixed gas. It's disappearing very quickly, but it's always there. But like a river, the water in the river is disappearing, but there's always water in front of you. So it's like a stalk sitting over the local area and warming it. And similarly, with particulates, local area gets cooled. We've also tried to look at the efficacy of policy changes to reduce nitrogen oxides, NOx emissions, and up until the Volkswagen scandal, that was very effective, and then they've just rocketed away again. So conclusions and policy implications: climate policy can be effective. It has a small cost at the aggregate level, but you have to address local losses, and Trump, of course, exploited that lack. At a global level, 1.5 is still preferable to 2 and just about achievable, but the costs of sea level rise to the end of the century are worrying. We're doing a paper for the Oxford Martin School on sea level rise and the enormous impact it's going to have in cities, the great big cities of the world, which are sinking because of pumping out groundwater at the same time as the sea level's rising. Major CO2 emissions reductions are needed to even begin to approach a net zero target, which we know is needed to stop the temperature to continue to rise. But there's lots of work going on out there. We've also created a new discipline, climate econometrics, which has now got roughly 60 to 80 people working on it worldwide, trying to bring in all these kinds of tools and empirical evidence to oceanography, to climatology, to volcanology, dendrochronology, geophysics, and even meteorology. And we're working with IPCC. In fact, my oceanographer has become one of the advisors and evaluators of the work that has been handed into IPCC. Thank you very much for listening.
Thank you very much, David. We have some time for some questions now. And I will ask you to show your hands and a microphone will come to you. But do please be aware this is being live webcast and filmed. So if you're not comfortable with that, then hold your question until afterwards. So Claire is there at the back. There's a question here.
In your 1.5 degree model of temperature, yes. In your 1.5 degree temperature model, why was South America affected much less than anywhere else in the tropics?
Yeah, South America is very lucky. It's also going to be much less affected by the sea level rise. But it's not going to be much less affected by the melting of all the glaciers in the Andes. That's a detail that couldn't be brought into this. But in fact, I've been several times to discuss it with the Argentine climate people, because the melting of the glaciers in the Andes would be a complete disaster for Argentine agriculture. On the other hand, one thinks of the Romans. The Romans managed to pipe water over enormous distances. The glaciers in southern Patagonia are increasing. Right? So you could actually imagine using gravity to get the water from there right up to northern Argentina, because it's not that much higher, right? So you just pump it up, and pumps are quite cheap, and get it there. But the effects are partly their closeness to the Antarctic. Now, the West Antarctic's melting at the same rate as Greenland, very worryingly fast. East Antarctic's actually growing. Right? The amount of ice in East Antarctic is going up. And that effect has a gravitational effect on the water, just the mass of the stuff, which pulls it away from Argentina and all the countries up to Brazil. And therefore, that's why they get less flooding. But they also get the very cold Gulf Stream, the Humboldt current affecting them, which helps offset some of this effect. And that's all locked in.
Thanks very much for the wonderful lecture, David. It's Stanislav Chmelev here. I was fortunate to attend the International Conference on Climate Change in Bonn, COP23. And the UK Minister for Climate Change and Industry came up with an initiative, together with her Canadian counterpart, which is namely to phase out coal. Yep. I was checking newspapers the next morning and the morning after, and how many of them have covered the event, do you think? None, next to none. So the question is more on the policy side of things. We have this very strange situation where, apart from a very few newspapers like The Guardian, nobody ever mentions climate change. And then also, there is so much that needs to be done still, even here. Energy mix is not 100% renewable. We have lots of people who drive cars which are not even hybrid. There's no high-speed rail. It's not electric, it's run on diesel. Energy efficiency in housing is, below standard in certain countries. There's an enormous potential to do much, much more. So, on your opinion, what do you think it will take to really make a more significant progress in climate change? Thank you.
Yes, that's a steady information of how bad it's getting has helped a lot. If you compare beliefs within the UK with beliefs in a number of other countries, say it's Australia, which hasn't had cooling, they've had some boiling temperatures, but they're still very reluctant to believe that being the world's worst polluter per capita and the supplier of most of the worst polluting materials in the world to other countries to do it. They've even abolished Gilead's wonderful green, clean climate change policy. So I don't know what it takes in countries like that, but in Britain there has been a very big move to accept it's happening. Now, many of the steps actually would save people money, like, as you mentioned, insulating their house. The government's tried to offer incentives to do that. We could, even although we're not the sunniest country in the world, solar cells are still pretty effective, and yet they've now come down to a price that households would only have about a 10-year payback. Well, you look at long bonds, they're not getting a 10-year payback on them, right? So there are many, many things that it's in the interests of the individuals to do, and they're not doing it. How you get the newspapers to change, I haven't a clue. I mean, I talk to journalists, and it just gets butchered. I mean, as you know, it's really hard to get them. They don't like the nuances, the finesse, the issues aren't all straightforward. And at the moment, I'm actually discussing with Prospect, based in this talk, having one of their speed reads on climate. And yeah, they're very keen to show it, but it's very hard to get them to show it the way it needs to be shown. So I don't know. And we've tried talking in the US. We've had a small climate change conference in the US with policymakers. And of course, they're all totally convinced it's happening. And New York can see that another Sandy would be a complete disaster. So it has taken the first steps. It's removed the spare generation equipment from basements up to lofts. It made the subway more resilient to flooding, etc. But Boston might be underwater by 2050, and Boston's done almost nothing. I mean, it's quite low-lying, and sea level's coming up. A big storm will come in. They will go further north. We know that. The hurricanes will not just reach New York, but will go further north. So, we try. We go, we give conferences, I give talks like this. I don't know how much impact they have.
Hi. I was just wondering if we've actually passed the tipping point? If you knew if we actually passed it?
I believe not. I'm optimistic that I haven't talked much about the dozens of ways in which humanity might save itself. It's walking along a tightrope, but it could be a Houdini, and it keeps walking for a very long time and saves itself. It won't save itself from sea level rise or some of the losses from temperature rise, but there are ways of extracting CO2 from the atmosphere, which were first discovered by paleoarchaeologists who went back to the Permian-Triassic Great Extinction. And they noted there were 1,000 parts per million carbon dioxide in the atmosphere at the time. 20 million years later, it's 250 parts per million. Where did it go? Because if it had gone into the oceans, there would be a carbonic acid that would have killed off everything. And it does turn out that as rain falls through the atmosphere, it becomes a weak carbonic acid, but when it lands in basalt, it dissolves basalt and forms a concrete. And the Icelanders are now experimenting with pumping seawater through air and spraying it onto basalt, and indeed it forms a concrete. And the concrete solidifies in 2 years. It's not a long-term thing. So now the question is, how expensive is it to do that, to extract CO2 from the atmosphere? Is the concrete usable? And so on. So there are directions like that. There are directions in which, for example, catalysts are being shown to be able to take even CO2 and turn it into an efficient energy source. via ammonia, for example. Mixing ammonia with these catalysts can be made into a fuel that's liquid, can go into cars, and when it's converted, it no longer pumps out NOx. It pumps out water and nitrogen. So there are solutions out there, and I don't think we're beyond the pale. Where I would define the pale is when we start to lose the tundra, and we start to get the emissions of methane on a scale that would match the huge Permian Triassic extinctions, that methane hydrates and methane in the soil have the same impact when they get pumped up into the atmosphere.
I wanted to know if you have looked at the rate of growth of real incomes in economies primarily driven by fossil fuels versus those primarily driven by renewable sources of energy. I'm thinking about, well, in particular, the role of developing countries in mitigating climate change and whether or not, from an ethics standpoint, they are allowed a grade of permissiveness in using carbon dioxide to rapidly advance their economies. So how do you see their role in addressing these issues?
I see their role as one in which the world needs about a 500 billion fund, which it gifts to China to build solar cells and windmills, which are the cheapest producers in the world, which then gifts them to all these countries, because most of these countries have lots of sun and often plenty of wind. And that would give them a source of fuel that's free, right, or almost free. All it needs is maintenance, etc. 500 billion is like 0.1% of the world's GNP. It's peanuts. It may sound a lot, but it's absolute peanuts given the problems. So I don't think we should offer, yes, we'll let you pollute more, because I think that's very dangerous. I think you'll get all sorts of game playing by big countries that use those countries to offset, which I haven't talked about. Britain has already done that. We've abolished manufacturing, we're a service economy. We import a lot of CO2 indirectly through all the things. I see you're using a mobile phone. Well, that took CO2, it wasn't made here, but we use it here. So we have to worry, but you could produce them without CO2, right? And that's the route we have to take. There's a question here.
I've got a couple of quick queries, if I may. The first one is the improved performance in the UK, the reduction in our CO2 production. Is that affected to any considerable extent by the reputed outsourcing to China and elsewhere of much of our production? And the other query is whether your modelling takes any account of the concern by Professor Wadhams and his Arctic methane emergency group of the possibility that the Arctic may be free of ice in the summer in the not too distant future.
Oh, yeah, it certainly might be. I mean, the temperature rises I've shown you. The Arctic's had several days this midwinter of +6 degrees, right? Normally it's frozen. So that's a real worry, and it's a feedback system that's getting worse. So I think that'll happen. But I don't think that's going to have much effect on the CO2 side. And yes, we do import a lot of CO2. Exactly how much is unclear, because we also export a lot of CO2. We export cars to Europe, etc. We export machinery around the world, all of which has some CO2 in it. But as the move out of coal has been the main reason for the reduction. There's been improvements in efficiency, so there's less oil and gas. If we can get out of oil, then we'll have a major improvement in our CO2 emissions. But we also have to get out of gas to get down to zero net emissions. And we're nowhere near achieving that, irrespective of imports, etc. But we are at least a reasonable role model for other countries to look at. And nuclear could be one of the solutions. I don't think Hinkley Point is, frankly, but small nuclear modules could well be the ones that nuclear submarines have used for 50 years without incident, could well be one solution. And it's one that also the people in Argentina are looking at to see if they can cut out their CO2 emissions. But agriculture produces it, cement making produces it, transport produces it, energy produces it, manufacturing produces it. We've quite a way to go, I'm afraid.
Thank you. Lieve van Woensel, EU Fellow.
Can't hear you.
Lieve van Woensel, EU Fellow at St. Anthony's. I have a question concerning the flights, you count CO2 production, including transportation, and I understood it's traffic, but what do you do with the air traffic?
In fact, up until relatively recent, the CO2 emissions are artificial. They're based on how much coal, given the known 2.67 units of CO2 per unit of coal, and the 1.6 from oil, right? So people look at what we used of those and they interpolate until recent times when we actually have started doing flask measurements. So it's all in there. If they bought their oil in Britain, it's not in there if they bought their oil somewhere else. But once we get the CO2 emissions, it's including everything. It also includes all the aircraft that fly in here as well as the ones that fly out of here. It includes ships that are producing it in the neighborhood as well as cars and locally. In fact, aircraft aren't the biggest problem. I mean, they are a problem, but compared to, say, agriculture and cement making, they're quite small. Cars are a problem, as I tried to explain how much CO2 we emit from our cars, even after catalytic converters, etc.
Thanks. I'm just observation that you focus a lot on 1.5 against 2 degrees of warming, and you sort of, there's 3 or 4 in there, but I'm a finance guy, and we spend a high degree of our time looking at the tail of the distribution, and there's a difference between, say, 0.1% or 1% or 5% probability at 4%, and how do you have a handle on that tail? Because that's the tail which, in finance, that makes you rich or kills you. And similarly in climate change, that's the one which either is going to be the really damaging one. How much do you feel you have a grasp on that tail?
Very little, because we don't know how much technology is going to affect CO2 emissions over the next 10 years. We think the tail won't take us out so far. We get a tipping point, which was one of the earlier questions. My close colleague, Rob Engel, of course, has looked extensively at tail probabilities through ARCH and GARCH and all these other DCC-type models, which can be applied in climate as well. And one of the problems is we don't have great data on many of the countries that really matter, by which I mean India and China. Right? India is probably going to be the slowest to move. China's moving very, very rapidly to decarbonize its economy, not just because of climate change, but because of the pollution it suffered from the particulate matter and the nitrous oxides it's pumped out. Now, if India starts doing the same thing, then the tail risk goes down dramatically, right? We don't look like getting to 4. On the other hand, if the tundra melts, 4 is going to look like a perfectly respectable outcome. So, and we just don't know. The tundra is melting in places. You go to any lake in Siberia in summer, you crack the ice, you light it, you light the methane. It's all bubbling up, and that's been known for 25 years. And the more it melts, the more problems. You get these sinkholes appearing. They're finding more mammoths because of it, etc. But it's a real worry. And we don't know how fast that'll happen. Colleagues at Miles Allen think it's not going to be terribly fast and isn't the biggest problem. It's our own anthropogenic emissions that are the problem. But again, the technology is there. I mean, we're, even in the US, despite all the beliefs people have about what Trump is doing, they have cut total emissions from coal by 25%. And that's been 500 megatons, right? That's roughly the whole of Britain's has been cut simply by reducing coal by 25%. That means you get rid of another 1,500 megatons of CO2 by getting coal out of their system. And there are very interesting studies that show that we may think fracking's a real problem, but the dropping in the cost of natural gas from fracking and the huge drop in the cost of electricity from renewables actually have an interaction effect on the use of coal in American industry. If either of them is cheap, it has a small effect on the use of coal. When both of them are cheap, it has a huge effect on the use of coal. And that's, of course, because different states in the US have different combinations of fracking and wind, right? And it's when you look at the aggregate for the US, you can see it's the interaction that's very important. Well, these are the kinds of things that we use our tools for. We do model nonlinearities, interactions, tipping points included. But tails, well, what's the probability of something you've never seen before?
One last question at the back.
You talked about compensating losers when there are policy changes. I wonder if you could expand on that.
I think we've behaved disgracefully to the mining communities since we started to cut out coal. I mean, these people, that was their job, it was often their children's job, the whole communities were there. It would have cost very little in aggregate terms to have sent in systems that tried to deal with the problems of those areas. And that's true in the US as well. Virginia has been decimated by the lack of doing things. Well, I mean, okay, there were coal miners. They could probably still build windmills, right? You give them the steel, the stuff, they just assemble them. There's all sorts of things they could do, even if Tibet's idiot suggesting they get on their bike and become butlers. I mean, it's just so silly. But that's the kind of view you get coming from government. And governments are very hard-hearted. I mean, the British government for the last time since 2010, when the Tories took office, have put bits of paper above people's lives. They just haven't cared about people. They've cared about silly things like what's the ratio of national debt to national income. Like it's been 2.2 in the past, it's currently 0.8. Oh, it's going to 0.81. Oh, we've got to worry. I mean, it's really hopeless trying to get governments to think rationally about how they deal with problems. And that's much worse than getting people to think rationally about climate change, I have to say.
Okay, well, thank you very much. I'd like just to draw your attention to some upcoming events before you leave. We have our termly lecture series on a Thursday. It starts actually not Thursday this week, but Thursday next week. And it's on science and populism, from evidence to narrative. So some very relevant themes that we've touched on. That's in partnership with the Oxford Institute of Population Ageing. So next Thursday, we have Dr. Andreas Sjodmark, who's head of the UK government's policy lab and a deputy director at the Cabinet Office, talking about how government needs to get better at policy making and to be more open and more connected with people. And the following Thursday, on the 17th, we have Science on the Front Line, getting good quality evidence into the news. And that is Fiona Fox, the Chief Executive of the Science Media Centre. And then there's a panel discussion the week following on putting science at the heart of society and culture. So there's actually 6 lectures in that series. I encourage you to look on our website, but some very relevant themes, and we'll picking up on some of the things that we've just touched on today. So there is actually now a drinks reception. So if you're interested in a glass of wine, you can turn right as you exit the room. Otherwise, you turn left. But I would just like to close by thanking David again for a really inspiring lecture, hugely complex material delivered with great enthusiasm and great clarity. So once more, thank you to David.